Right, I just want to talk about the answers to questions 7 and 8 from exercise 8C. And these, I would say, are absolutely crucial in terms of the most realistic, most authentic type of differential equation that you'll have to solve. This is, well, look at it. It's forced harmonic motion and it's damped at the same time. That's exactly what you come across when you are coming across actual real life modelling of an actual situation. And the one example that I always think of is this, right? And this is what I would always say is if ever you're sat on a bus and you sat at the lights and you look at one of the posts that goes on the floor to the ceiling, it starts vibrating. And just as the driver's got his foot on the accelerator at a particular frequency, it starts vibrating more, and we call that resonance. And that word resonance, it's a proper word, an English word that you use, but that is forced harmonic motion because the frequency at which the engine is vibrating because of the driver having his foot on the accelerator, that frequency is what the bar is being forced to vibrate at. But then it has its natural frequency. If it was stationary and you just knocked it, the frequency that it naturally vibrates at, and that's the natural frequency of the bar. But obviously, it's stopped from moving by the fact that it's screwed into the top and the bottom. So all of that comes together in that situation and would lead to an equation that would be, recognisably of this form. So this is question 7, and it's a really nice question. It's not too tough because, like I was saying, just solve the differential equation, and that's what you end up with. Don't worry about what that means. We know what they mean. We're all over what they mean, but don't worry about it. Just solve it, and you end up with the solution. Particularly in this question, it's just a case of solving the differential equation and substituting in the initial conditions. So here's the complementary function. There's its solutions. This is nice. It's a nice easy one, isn't it? When it's real solutions, and then it's this. We would call that heavy damping, wouldn't we? But there you go. And then particular integral, I'm looking at that. It's a constant. So what we're going to do for our particular integral, we're going to try x equals lambda. So try x equals lambda, and I've written there, it might not, I should have made this bigger. There we go. Yeah, sorry about that. Right, so, try x equals lambda, x dot and x double dot equals 0. So, 6k squared lambda equals 5k u, alright. Yeah, that's just subbing into here. 0 and 0 and 6k squared lambda. So lambda equals 5u over 6k. So there's our general solution there. X equals this is our general solution. And now I'm working out the x with dt because we're going to sub into the question the initial conditions. So there's the x with dt. And then I think this question's a bit sneaky because when I first looked at it, I thought it was at rest because it says it's at rest. And but then it says, and then it's moved, so it's not at rest. Is that what it is? Yeah, the end of the spring is then moved with constant speed u. All right, yeah. So anyway, that's saying that the x when t is 0, the x dt is u. So there we have our two equations there. Do you know what I've done here? I've just times it and divided it by k, and moved these two over just so that it's in that form, so that I can. Mary, not that quick at doing simultaneous equations in my head, but what did I do? I did equation 1, take away 2 equation 2's. That's what I did. Yeah, there's equation 1, take away 2 equation 2's. So, year 9, simultaneous equations. But, there you end up with working out big, and then it worked out, that's in the way there, the general solution. But it's not hard to see, is it? It's, where is it? There. So it's minus 3u over 2k, e to the minus 2kt, plus b, 2u over 3k, e to the minus 3kt, plus 5u over 6k. That's it. And all we've done there is solve the differential equation, and that's it. Not really a context to worry about. Right, let's have a look at the next question. Number 8. Okay. Hang on a sec, sorry about this. What? Oh, that's the download that. Sorry about this.
Sky Mobile also gives spare data so you can share it with your family. Sky Mobile.
No, why that's been said, they just took the exact same photo.
Play Auto, pay all wins and bonuses in cash, restriction free. Now that's fair. Discover fair play.
Right, I don't know if you can still see this, what I'm talking about, because I can't see myself here. But right, this is the. Oh, I didn't even really read the question. I just solved the differential equation, which is the advice that I always give: is just solve the differential equation. But I didn't find a particular solution. It just said, right, there's our complementary function, and it solved it. And then the particular integral, because it's 100 cos t. I tried x equals lambda sine t plus mu cos t, worked out x dot, worked out x double dot, subs everything in, got these simultaneous equations and then solved them. So there it is there, and this is the end of the question. I suppose that's part A there, really, isn't it? But then part B, show that a particular solution, here's what's the general solution, there's my general solution there, x equals a to the minus a half t plus b e to the minus t plus 30 sine t minus 10 cos t. Okay, that's part B done. And then part C, I'm just subbing in the information, which is what t is naught, x is naught, and x dot is naught. This is not obvious from the question. I think you need to infer that a little bit. Just read it carefully. But anyway, having done that, then I sub in t is naught and x dot is naught, and get these two equations. A plus b equals 10 and a plus 2b equals 60. So then b is 50 and a is minus 40. And when you sub in, there's your particular solution. When you sub in t is 5, you get the disconcerting answer of minus 34.55 metres, which I didn't really like. So I actually checked the back of the book there, and it turns out that was right. So there's the answer to that there. Where I am back. So that's what you get anyway with that question. But they're supposed to be as are. Well, I'm not being rude there, saying they're supposed to be, implying that they're not, but they are just solve the differential equation. Right, what I intend to do next. I wanted to say something here about the previous question. Right, sorry about this. So on this previous question, I wonder, right, what would be the behaviour of this motion as t tends to infinity? I wondered if you could have a think about what that is. So t tends to infinity. What is the behaviour here? And it's interesting that it's heavy damping, but it's being forced to oscillate at a particular frequency. And it's an interesting question to ask there. And you know what? I'll ask the same question about question 8. So what is, hang on a sec, what is the behaviour on question 8 of, I know it's sideways, like, but, right, there's our motion there. So as t tends to infinity, again, this is heavy damping. So what is the behaviour of it's a piston. What's the behaviour of the piston as t tends to infinity? And again, it's heavy damping, but it's getting forced to oscillate at a frequency that we can see here. So it's an interesting question to think about. And we'll talk about the answer I'll tell you the answer next time I do something like this. And I'll tell you what I want to do. I'm not going to immediately move on to the very last thing actually, which is the most useful type of differential equations that there are in the world. You know, when people who actually use differential equations in the jobs. But what I want to move on to before that is I just want to show you a physical derivation of this damped, forced harmonic motion. So that's the next thing that I'm gonna look at. Okay, nice one.